And another interesting algorithm is eigenvalue estimation. So suppose you have a state psi, which is an eigenvector of an operator q. Now you want to measure the eigenvalue of the operator q. So what you can do is you pass psi through q through the control q, like something, a setup like something like this. Suppose, so here you have 0 plus 1, and this denotes control not gate, which is whenever the qubit is 0, it won't act anything. Whenever it is 1, it acts on q. So at this stage, the state together will be something like this. But after this, what happens is it becomes, whenever it is 0, the psi remains as such. But whenever it is 1, then q acts on the psi. It will be like this. Q acts on the second qubit. Whenever the control qubit is 1, q is acting on it. So your superposed state will be something like this. Now suppose q is an psi is an eigenvector, then this becomes, at this position, this becomes 0 plus lambda times 1. Because q times psi will be equal to lambda. So q times psi equal to lambda times psi. So this state nicely comes out to the first qubit. And then later we can do some tricky processing on that qubit and try to measure lambda to certain accuracy. So which means we measuring lambda is equivalent to the same as measuring the eigenvalue of q. Okay, so you do this with some good number of accuracy, and this is the accuracy. So so this is the accuracy and the closeness of the result with the actual result. Okay, and if you see, the complexity will be proportional to 1 by epsilon, where epsilon is the accuracy that you wanted. So if you wanted epsilon close, your lambda to be as close as the actual lambda, then you wanted to run the algorithm proportional to 1 by epsilon times. If your a hat minus a, this magnitude should be less than epsilon, then you have to run the algorithm 1 by epsilon times. So if you want perfect accuracy, then epsilon should be equal to 0. Then you have to run it infinite times. There is no, you cannot achieve it in a perfect accuracy. So you should relax some amount of noise in the eigenvalue estimation, and that will help you to speed up. Okay, and this will help you to find the eigenvalue of an arbitrary matrix too, without knowing the eigenstate. If you pass an arbitrary state, then also there is a tricky statement that you can convert the top measurement as the eigenvalue, because once you measure it, the state gets collapsed to one of the basis state, and here it will be superposed state of eigenstates. So it will project it to one of the eigenstates. So you nicely measure it on the top, like so you do something and do measure the eigenvalue of the particular matrix. Now this is another version of it to increase the accuracy. Okay, and so these are two basic applications like for quantum algorithms. So first one is to try to find out to search a specific candidate or specific person or specific candidate with certain properties. And second thing is to improve to find out the eigenvalues of an operator Q. Okay, and another interesting application that we are now working on is called reinforcement learning. So I will talk about reinforcement learning a little bit. Before going to quantum reinforcement learning, I will talk about classical reinforcement learning a little bit. Okay, and classical reinforcement learning is more about how we learn cycling. So we learn different things. We learn alphabets. So we learn alphabets like a machine learning. Like we are imported with the data. So we learn lot of words in the beginning. During our childhood, we learn lot of words and their meanings. And once we grow up, we try to read the words ourselves, new words ourselves, because we are trying to read some more and more words in our childhood. So we can do a complex, we can read a complex words later on. Okay, so that is a classical machine learning kind of thing. You have a collection of data, and then you read the data according to that, and then you train your brain accordingly, and later on you read a new information based on whatever the detail that you have in mind. And reinforcement learning is slightly a different version of learning. Here we learn, here it depends on how we learn cycling. So how we learn cycling, we don't see someone who is riding cycle, or we don't get the process into your mind and do it. But if you want to learn cycle, you have to learn. You have to go to take a cycle and you have to pedal it. So once you pedal it, you will learn. Like so, one if you are trying to fall on left hand side, by nature you push your handle towards that direction so that you balance yourself. You try to balance yourself. So you practice it again and again. In the first few points, you may make mistakes. You may not push it on a proper angle, or you may not push it on a proper speed enough to maintain the balance. So you will fall down. Like so, your action will fail. So you will get a reward. A reward in the sense you fall down and you got a negative reward, or you move on and you get a positive reward. So you get a reward, and based on the reward, you change your angles. You change your the positions. You change how you alter your angles and how you speed the pedal, right? Based on that, you learn it again and again. And once you learn it, after that, you will be able to ride anywhere, and your muscles will be trained accordingly. So that's the idea of reinforcement learning, where we don't have any data prior, but you directly go into the environment and take some action and see what you get. And based on what you get, you try and do the next level of action. You change your action accordingly. Okay, and mathematically, so if you want to explain it in another form, we can think of like, suppose you have three choices. You choose arm 1, choose arm 2, choose arm 3. So you choose, you are given three boxes, and box 1 has some amount of money, box 2 has some amount of money, and box 3 has some amount of money, and you are allowed to take several number of times. Okay, then what will you do? So at first you don't know what the reward is hidden behind each arm. So first thing is something called as exploration. You just go and see. You just go and open arm 1. See, since you do not know about all the arms, you go and choose arm 1. So now you choose arm 1. You get 1 rupee from arm 1. Okay, and you got some reward. Okay, fine. It looks good. So there are two more arms which you haven't explored. So you explored arm 1. You got something, and it's fine. And now you know about arm 1. So there are two chances. You can stay with arm 1, or you can go to arm 2. And now since you have so much amount of time to chances to pick arms, you go and pick arm 2. Arm 2 will give you 5 rupees, which is higher than arm 1. So now you know about arm 1 and arm 2. So now you know among arm 1 and arm 2, you know arm 2 is better, but you don't know anything about arm 3. So the next natural choice is go and try arm 3 once, and you may get 10 rupees. And after this, now you have explored enough. Now you exploit your knowledge. So now you have explored it, and you have some knowledge that arm 1 gives 1 rupee, arm 2 gives 5 rupee, and arm 3 gives 10 rupee. And hereafter you pick arm 3 every time, because arm 3 is giving you the best reward. So you pick arm 3 every time continuously, and you get the higher reward. Okay. And a slightly different version of reinforcement learning is your arms are not deterministic. That is the problem here. So your arms are random. Like so, you pick an arm, you pick a box, and the box will give you a reward of 5 rupees with the probability 0.7, and no reward with probability 0.3. And similarly, arm 2 will give you a reward of 5 rupees with 0.3 and no reward with the probability 0.7. Arm 3 will give you a reward of 5 rupees with the probability 0.5 and no reward with the probability 0.5. Now, which arm is better in this case? So, if someone who is looking into just the picture, they can clearly say that the arm 1 is better, because the probability of getting higher reward is higher there in arm 1. But since we do not know this probability a priori, now we have to learn these probabilities. How can you learn? You pick arm 1. Now, once you pick arm 1, you mention about this arm 1. Okay, and you explore arm 1 for some time, and you try to understand the distribution of arm 1, probabilities of arm 1, and then you go for arm 2, understand the distribution of arm 2, go to arm 3, understand the distribution of arm 3. Now again, this arm 1, arm 2, arm 3, the distribution that we understood, since it is done by trial and error method, we toss the coin or we choose the arm several times and read it. This may not be exactly equal. They are approximate. So to manage this approximation, so what we will do is we do exploitation on one side, and at the in between we will go for exploration. We will try to read arm 1 for some more time to get a better accuracy about the results of arm 1, and try to read arm 2. Though in between we exploit arm 1, And at certain point, we will go for ARM 2 and try to explore it further to get improve the accuracy about information in ARM 2 and come back to ARM 1, which we are exploiting. Sometimes while exploring, we may accidentally pick ARM 2 because the data may give you the numbers may be different, because there's a good chance that you will get more number of success in ARM 2. So you can choose ARM 2, which is bad also. Like so, and then because ARM 2 is not pretty accurate, you try it again and again. The accuracy improves. That is, as the n goes to larger and larger, that n by n, capital N, becomes probability. So that is the law of large numbers that you might have learned, and somehow that we try to push it towards probabilities. Okay, and this in play between uh, exploration and exploitation is reinforcement learning, and the goal is we want to achieve the optimum arm very faster. Like we want to fix with arm 1 faster. So if you know arm 1 from the beginning, then it is better. Every time I will choose arm 1 and get better rewards. If I choose arm 2 and arm 3, then I may get poor rewards, which means I have to regret for choosing a different arm than the optimal arm. So I may get a different probability. Okay. And similarly, there are certain other cases in reinforcement learning. I'm going to skip this slide. This is like this motivating this expected reward. We don't focus on the reward since it is probability distributed. Instead, we focus on something called as expected reward, which is the average reward in each that we can achieve from each arm. Okay. And yeah. So one interesting algorithm for in classical sense is per confidence bound algorithm. So what they do is they toss it, they explore every arm, toss every arm one by one, and exploit the arm which has maximum UCB, which is called as upper confidence bound. And UCB is computed as mean plus some function of n comma ni, where n is the number of times you have run the algorithm, and ni is the number of times you pick the arm. Okay. So the idea of alpha is if you run the algorithm many times and if you have picked the arm I very lesser number of times, then this alpha should be higher, so that you may be able to pick this arm also. The chance of picking this arm also can be increased to support exploration. Okay. So for that goal, we instead of just choosing the maximum mean, we choose the maximum of mean plus this alpha of n plus ni for each. Okay. And classically, it is bounded by Chebyshev inequality. The accuracy will be bounded by Chebyshev inequality. This says this inequality. I'm not going into the detail of this inequality. This inequality says that this ni should be proportional to epsilon 1 by epsilon square, so that the denominator gets cancelled out. So ni should be proportional to 1 by epsilon square to get a better accuracy. So if I want to get an accuracy of epsilon, you have to run the algorithm on big O of 1 by epsilon square time, which is higher in the sense of classical sense. And in the quantum sense, what we can see is it can be done by using just 1 by epsilon iterations. And the quantum reinforcement learning, in quantum reinforcement learning, the problem setup is we model each arm as a quantum unit. So each arm 1, the reward that you obtain out of arm 1 is modeled using a quantum operation that is denoted by this translation. O1 translates 0 to something like this, and similarly O2 translates 0 to something like this, and O3 translates 0 to something like this. So you model the arm in terms of these operators, which translates 0 to appropriate distribution. You can see that this is clearly, if you measure here, then it is clearly 1 with the probability 0.7 and 0 with the probability 0.3. And it is similar to the one that is mentioned for the classical case. Okay. And now you do the exploration here, and the result here is this one. So the y-axis here represents regret in the sense that I feel bad for not choosing the optimal arm. So this is the reward for optimal arm minus the reward that you obtain. It's proportional to something like this. Okay. So regret says some number that says that I feel bad because I choose a suboptimal arm which is not optimal. Okay. So that's what regret is. And now as I choose the arm several times, in classical sense, you can see the regret increases and try to get converged it takes a longer time to converge. And quantum sense, you can see that it gets converged very faster. So So it converged faster for this case. Okay. So it very faster it converges the regret, and the regret is very small, much smaller than the classical sense. So you get so regret is much smaller in the sense the reward will be higher. Regret and reward are inversely proportional. So lower regret implies that you are getting higher reward. Okay, and that is what the quantum UCB helps in. And if you see mathematically modeling, this one gives a speed up of 1 by epsilon. That's what we have found in the quantum UCB. Okay. Yeah. So if you have any questions, you can feel free to ask now. Like I will take a short break again. So with this, we will stop discussing on quantum algorithms. So in quantum algorithms, I will discuss three main algorithms. One is two algorithms that are developed very long back, that are started very long back, which is quantum search and quantum eigenvalue estimation. And another algorithm which is a port of classical reinforcement learning to quantum reinforcement learning, which we are working on. So if you have any questions, feel free to ask. I will wait for 1 minute or so.
Sir, there is some questions arise in the chat box. Shall I read it?
Yeah, please.
First question is, what challenges exist in implementing fault-tolerant quantum systems?
Okay, I will discuss that soon. So that is the next topic I will talk about it, like error correction, where we try to impose fault tolerance.
Okay, sir. The next question is, which software can be used for quantum computing implementation?
So quantum computing implementation, we have to go for the software that is provided by the whoever have developed the hardware. Mostly it is Python, the QuizKit, IBM's QuizKit, or Pennylane, or other softwares. They run on Python for now. So QuizKit, you should be careful. Like QuizKit, there are two things: quantum simulation and quantum implementation. So you can simulate computer as long as the number of qubits is lesser. Okay, but though it will take more time than the classical algorithm, the quantum algorithm in a quantum system. That we call it a simulation. Okay, so in a normal computer, whatever you do, if you run a Python in a normal computer, then it is called a simulation. And implementation, we call it as implementation when we implement in a quantum hardware, because classical quantum hardware does not support quantum algorithms directly. So we have to go for quantum hardware, and quantum hardware we don't have access. Not everyone will have access that quick. So this IBM and Pennylane, they are giving access to their quantum hardwares. So if anyone interested can get access from them. They are giving very small number of qubits for now for free, and for large number of qubits you have to pay for it. For real-time implementation, you have to get the hardware access, which is not accessible for everyone. So most of the time we do software simulations. In terms of algorithm, the simulation is same as implementation, classical algorithms, because classical algorithms are implemented in classical computers. But quantum algorithms are implemented in quantum computers, but we don't have quantum computers in our hands. So implementation perspective is you have to get the hardware component from the IBM or Pennylane or someone who is working on it, and Rigetti or someone like. So if it is a software component, we can develop our own component, or you can use the softwares that are developed by IBM, Pennylane, or the one that I heard that recently IASC and IIT Roorkee are working on developing a software for the same. So you will get software soon, or you can also develop your own softwares for simulation.
Okay, sir.
Preferably Python. Most preferable software is Python, because many research algorithms comes in Python language.
Okay, sir. And the next question is, each qubit will have a measurement plane. If so, receiver on receiving the data must be aware of the plane for each qubit also. So, the sender must send the measurement plane for each qubit.
Yeah, sender should send the measurement plane for each qubit. But the point is, once you share the qubit, when the qubit is in progress, because of no cloning theorem, the third party cannot copy the qubit and take a copy with him. Okay, if he takes a copy, it can be detected by the receiver. So they can throw that qubit at all completely, saying that it is compromised qubit. The remaining qubits which are uncompromised, which the sender and receiver has already shared, they have the qubit, and now the sender can announce the measurement plane in public also. Because even if the third party knows the measurement plane, now he don't have the qubit to measure the plane. So he don't know what to measure. Like he don't have the data on what to measure. Okay, so the receiver alone will have that data on what to measure, so they can measure on his own plane, like on the plane that is being announced. So yeah, it should be shared, but it can be made public once the qubit is shared between both of them. Okay.
Okay, sir.
So have I answered?
Yes, sir.
Okay. Any other questions?
No more questions, sir.
Okay. Okay. And the next part I want to talk about is quantum error correction codes. Right? So why quantum error correction codes? What is the significance of this? Why fault tolerance? What do you mean by fault tolerance and so on? Okay. So and this will help you to give an idea on how fault tolerance can be implemented. So the first thing is I want to start with classical codes. What we do in classical error correction codes. Maybe some of you will be working on classical communication or classical channel coding or classical error correction codes, and you may be aware of this classical codes. Though I will give an introduction on what a classical error correction code is. Now I think you have very big space. You have a very big space that is as shown in the oval, and now you want to send some information. Where do you put your information here? So for example, I can put my information this close. This is 0 and this is 1. I can put my information like this. But now what is the problem? During the transit, the noise can push this 0 to this 1 easily because they are placed close together. So the noise can affect it each other. So what I will do is I will put typic 0 somewhere here and 1 somewhere here, which are too far away, 2 points that are kept far away. Okay. So I'll put 0 and 1 somewhere here, so that if there's a noise affecting this qubit, it should affect heavily. You need a heavy noise to push it to the region of 1. As long as the region don't intersect, any point here, any point from the receiver side in this region, we'll call it as 1. Any point here, we call it as 0. That is the receiver detection criteria. Okay. So the idea is you have to keep it as far as possible. That is the whole point. A simple example is you map 0 to 0, 0, 0, 1 to 1, 1, 1. This is called as a repetition code. The classical single bit 0 can be encoded to bit 0, 0, 0, and bit 1 can be encoded to bit 1, 1. Now, if someone want to push the bit 0 to bit 1, they have to push 3 bits. They have to push first bit to 1, second bit to 1, and third bit to 1, which is slightly challenging. As long as there are 1 bit, if there is 1 bit flip, then we can correct it. We can perfectly correct the noise in it, right? So you can take the majority logic. For example, if it is 0, 0, 0, and there is a 1 bit flip, you will receive as 1, 0, 0, or 0, 1, 0, or 0, 0, 1. Now you can take the majority logic. Here you have 1, 2, 1 ones and 2 zeros. So you can say there are 2 zeros, so this should be 0 and not 1. So you can also, with this, you can correct every single flip error for every block of 3 qubits. Okay. It's now the thing is the idea is you keep the points as far as possible. That is a catch here. Okay. And there's a class of error correction codes called linear block codes, which is defined by something called as generator matrix G. So, for example, in the repetition code that I was talking about, the G is 111, and this X is the code word is founded as something like G transpose M, where M is my message. Now, for example, you have 111 G transpose. When the message is 0, it is multiplied by 0, which gives you 0, 0, 0. When the message is 1, it is multiplied by 1, which gives you 111. So 0 is sent as 0, 0, 0, and 1 is sent as 1. And this is the structure of a linear block code. And there's a different picture for the same linear block codes, which we call it as parity check perspective. And for the same code, you can represent by another matrix H, and represents the code words as set of X such that H times X equal to 0. So if you try to solve this equation H times X equal to 0, if you try to solve this system of linear equations, you can solve it using Gauss elimination or any other method. You will find that X equal to either 0, 0, 0 or 1, 1, 1. So assuming binary transmission. Okay. So you have X equal to 0, 0, 0 or 1, 1, 1. So which means the code space, the options that we get here and here both are same. So you have both keys. So you can represent the code word in another form, which is like set of X such that Hx equal to 0. Okay. So these are the two perspectives. And in quantum sense, the parity check perspective is highly relevant. Okay. And the class of quantum codes are called, that we are focused on, are called as stabilizer codes. And so these stabilizer codes are quantum analogous for linear block codes. You will have a parity check matrix H, and your interesting code words, like you detect errors by using finding the terms for which your H times X is not equal to 0. If H times X equal to 0, then we don't say that there is an error. We assume that X is a transmitted word. And if H times X is not equal to 0, then we call it a some syndrome, something like this. Okay, this syndrome. And using this syndrome, we find out which error has happened. So, for example, in this case, if we take H times 0, 1, 0, 0, as we did in the earlier case. So this is same as 1, 0. Once you receive 1, 0, you can clearly say that the bit flip is happened at 1, 0, the first bit. Okay. And similarly, if you see sending 1, 1, 1 and getting a bit flip on the first thing, the H times 1, 1, 1 will be 1, 0. It remains the same. If you see, calculate this, because the bit flip error at the first flip will give you the same syndrome. Okay, it don't detect the code word, but instead it detects the error. Okay, so it helps in detecting the error. And the decoding problem in classical sense is given X, so given S and R, there is syndrome and the received code word, because you receive some vector, the code word, and from that you have to find the error. So given that you have received something and you have computed a syndrome, yes, you have to estimate the actual word that is being transmitted. So that is the goal in the classical sense, the decoding goal in the classical sense. So in quantum sense, we have a code word C, which you call it as yeah. So yeah. So we have this notion. Just recalling the classical sense in the first two lines. C is an additive group in classical codes, and C is set of X such that H transpose X equal to 0 for all H in C triple. So I'm trying to change the notion here. So earlier I have talked about H times X equal to 0. Now H has, say, 1, 1, 0, 0, 1, 1, this form, X equal to 0. This is equivalent to saying that 1, 1, 0 times X should be equal to 0, and 0, 1, 1 times X should be equal to 0. This I call it as H1 transpose, and this I call it as H2 transpose. So now I do the same thing in a different form, that is H transpose times X equal to 0 for all H in C perp. C perp is some other state that is spanned by this H matrix, the rows of H matrix, which I'm going to ignore. But the whole concept is this: H, instead of computing seeing the whole matrix, you see row wise. The first row times X equal to 0, second row times X equal to 0, and so on. Okay. And this notion directly translates into quantum code, quantum stabilizer codes. And this is defined by set of stabilizers. Stabilizers are certain Pauli operators. Okay, so a group of n qubit Pauli operators. And we define code as a +1 eigenstate of this stabilizer, like something like this. Your code word will be set of psi such that S times psi equal to psi. For all S in that particular group called a stabilizer. Like similar to that of H in C perp, we have S in particular group called a stabilizer group. Okay. So that's what we call it as quantum code. And yeah, we can see a small example so that it helps us to understand the quantum code. And we can think about a stabilizer that is generated by a 4 qubit stabilizer generator, generated by all identities X on all qubits, Z on all qubits, and Y on all qubits. So this is a 4 qubit code which has the ability to encode 2 qubits. Okay. Now, if I try to find the code space is set of all vectors that are neutralized by this. So, if I take all these vectors and if I apply xxxx on it, and there won't be any change. It remains the same. For example, take xxxx on 000 plus 1111. So this is x on all four, which means this will be converted into 1111, that is acting x on this, plus this will be converted into 000. As earlier I have told you, x acts on 0 and converted to 1, and x acts on 1 and converted into 0. And so it does this. Okay. So now if you see, this is same as the earlier one, 0000 plus 1111. It does not change it. So extend psi remains as psi. So it don't alters it. Okay, these are called as stabilizers. So you define the code word like this. How will you detect the error? Suppose you have an error xia. Now you detect error by checking whether it commutes or anti-commutes in the stabilizer. So suppose you have an error like this, and then you measure this stabilizer, z, and this stabilizer will give you a -1 eigenstate, -1 eigenstate. Earlier it is a +1 eigenstate. If it is not, there is no error. If it is a error, if there's a error, it will give you a -1 eigenstate. Okay. So it is like you are detecting here. So in the classical repetition code we have seen here, if the error is say 0 1 0, that is bit flip on the first qubit. Now this will be same as H1 transpose X will be same as 1, and H2 transpose X will be same as 0. So this will say that there is some error. So you have to see, look into that. This says that there is no error. It's okay. Okay. So now similarly here also, this operators will help you to detect the error by checking whether it's a +1 eigenstate or -1 eigenstate. So if your S times psi equal to psi, it will say that there is no error. If the S times phi equal to the -5, then it says that there is an error. So now your focus is more on errors and not on code words like the classical code words. So classically we have given R, you have to find given R and yes, you have to find the error. Now here you have only yes, using yes you have to find the error. So the classical code, the problem is H transpose E equals 0 or H transpose E equal to 1 depending on the orthogonality or depending on the presence or absence of error. And here your E times psi will be equal to psi, or E times psi will be S times psi will be equal to psi, or S times psi will be equal to minus psi depending on the presence or absence of the error. And there's a tricky circuit which computes this eigenstate, and we have discussed this earlier, which try to compute the eigenvalue of an operator if you know the eigenstate. So this circuit will help you. Okay. And now if you see the decoding problem, here the decoding problem is you have given error, you have to find the syndrome. So this is a particular example for codes. And now the thing is, you have a connection between classical code and quantum code. So suppose you take this stabilizer, IIIX is generated by this group. And if you see, take only these two operators, a product of these operators will give you the entire set, the entire stabilizers. So if you don't apply any of this, it is identity. If you apply X alone, this is this, C alone, this is this. And if you take both of them, product of this will be YYY. And because that is the XY is proportional to Y. Sorry, X set is proportional to Y. Because of this property, the product of this will be YYY. So you will get, so this particular codes with the stabilizer space is generated by these two vectors alone, these two errors, these two operators alone. And these two operators can be represented by matrix form, where this is called a symplectic form. And you think about the first row. First row, I apply 1 on all first 4 qubits, first 4 columns, because it's X on first 4, and it is C on first 4. So for the second operator, it is nothing, no X component is there, so it is 0 here. But C component is there, so 1 for here. So it's like if you have, so you map every Pauli operator with a tuple, where if it is X, you map it with 1 0. If it is C, you map it with 0 1. If it is Y, you map it with 1 1. So that is a mapping. So this is the first qubit. The tuple corresponding the first qubit is first, and this one. So 1 0 corresponds to x, 1 0 corresponds to x, 1 0 corresponds to x, and 1 0 corresponds to x. 0 1 corresponds to C, 0 1 corresponds to C, 0 1 corresponds to C, and 0 1 corresponds to C. So you map the generator in the form of parity check matrix. And the interesting fact is, I am going to skip this math. Okay, so I will tell you the final conclusion of this discussion. And the conclusion of this discussion is: suppose you have an error E, then your H times lambda E will be equal to some syndrome, and this syndrome captures the information about the error. So now our decoding problem is identify E given S. So this is, looks like similar to that of a classical error correction. So there's a lot of connection between classical error correction codes and quantum error correction. Okay, so this lambda is a constant matrix given by this. Okay, using this symplectic form, we can convert this commutation anti-commutation relation into this matrix multiplication, which is a classical error correction code problem, decoding problem, except that you don't have R. You cannot read the information that's being received. And there are other class of classical error correction code, which is called a CSS code. I am going to ignore this part. The one definition is you have the parity check matrix in two form. One set of stabilizers which access X alone, and other type of stabilizers which access V alone. And if you have certain property, then you can call it as a stabilizer code without any issues. And this will help in simplifying the decoding. And now I will talk about fault tolerance. So I think someone asked about fault tolerance there. So I'll talk about fault tolerance here. Now during this operations, we have to do some measurement. So for example, I wanted to measure the eigenstate of XXXX on the state phi. So what you can do is you develop a circuit something like this, where you add an ancilla qubit, and this ancilla qubit will give the measurement outcome. So you push the measurement outcome, this XX information about this eigenstate of XXX into this last qubit, and measure the value of the last qubit. So this is the simple circuit that does the measurement. But the problem here is, suppose there's an error here. Suppose that there's an error because of a faulty device here. See, and now because of this C0, this error back propagates into your data. Your data is getting corrupted more and more because of this ancilla qubit that is being added. The error in the ancilla qubit that is being added, which should not affect your data, but it is affecting because of this circuit. So now this measurement circuits should be devised nicely, like something like this. This is called as a Shor measurement scheme. It's a nice scheme in which you don't propagate it back. There are different other schemes. This is one of the scheme. Okay, so you don't propagate the errors back. So if there's an error here, it will push back only into the measurement outcome here and not to the data back. So if you have error here, it will push to the measurement outcome here and not to the data back, because there is no more CNOTs there, no more connected gates there. Okay, and we wanted to develop these kind of measurement components. So for this, I wanted this stabilizers to be of low weight. If this is of high weight, then you will have more number of CNOTs. You need more number of ancilla qubits to impose this particular thing. So if there are weight of this is, say if it is acting non-trivially on say 100 qubits, then you need 100 ancilla qubits to develop this circuit. So it's better if you have stabilizer generators has a low weight. So this is the connection between LDPC codes and the fault tolerant computation. Okay. So another aspect is fault tolerant computation. Now you have the state, you have the actual information, say alpha 0 plus beta 1, and you protect it using a quantum qubit, like so using multi qubits. So you have alpha 0 0 0 plus beta times 1 1 1. You protect it using a repetition, but some error correction. Now you have to develop a quantum algorithm on this encoded state, because if you want to go back to the original information like classically we do, then you end up in a highly noisy terrain to do a algorithm. So you don't want to go back to the original information. You have to do computation in the protected information itself. So to do computation in the protected information itself, so you wanted to implement some interrogate. Okay. Now you can develop these codes differently so that the certain interrogates can be implemented like this. Like for example, if I want to implement a logical X, you act X on the first qubit, X on the second qubit, and X on the third qubit. So X on the second qubit, first qubit, X on the second qubit, and X on the third qubit. So all over it will give you an X on the logical state. X flips logical 0 to logical 1. So if you develop error correction code such that your algorithm is implemented like this, then a noise here will not propagate to the other codes. But not all codes will support this. You have codes that supports unitary operators like this. For example, if you take a different type of gate, so I'm not talking about that now. So if you try about a different type of gate, you may have to implement it on a block diagonal form, something like that. So which means if you have an error here, that nicely propagates down, and it propagates down, it propagates down, it propagates down. So in a protected state, when you put up any quantum operations, the noise gets propagated throughout the code. Well, which harms the code, because you will have capability. In the first figure I have told you, like, so the ability of error correction, it depends on how far you keep the qubits. Now you kept it quite far, and now this noise, because of these gates, pushes it further closer. So it pushes more further closer, and they become merged up. So this propagates the noise, or it amplifies the noise without affecting the information. So that is a problem here. Okay, and practically we focus on this kind of circuits where we have parallel kind of block diagonal kind of implementation. Noise here is cannot propagate to the other blocks; it will propagate within these blocks itself. So we target something like this when we focus on fault tolerant computation. And these fault tolerant error corrections are supported by a class of codes called the quantum topological codes. And these days, many quantum computers that we learn in news and all, so they work on this surface codes, a class of topological codes. And how do topological codes work? So you place the qubits in a physical space, something like in this picture, you can think about the dots in this picture, and your qubits are placed on the dots, and only the qubits that are placed together, they form an interaction. Like a check operator. Suppose you want to measure a stabilizer, then you don't go and measure every stabilizer there. You don't go and check all the qubits. You check only the qubits that are located in this locality. So you check only those qubits and see whether there's an error happen in this locality or not. And you do similar checks on all the qubits like this in a mixed form, and together you form a single error correction code. And the information is encoded globally, and the local errors can be detected. Okay, and surface codes and color codes are two basic examples for such topological quantum codes. Okay, we'll talk about surface codes. Surface codes are defined on certain graphs, something like this. You can think about it. And for example, qubits are placed on edges. So these forms the edges, qubits, and these nodes forms the checks, and which means this node will check whether the sum of this qubit, this qubit, this qubit, this qubit, sum of these 4 qubits are 0 or not. Okay. So this check on all nodes will give you a local check, and everything together will protect your information, protect your global information. Okay. And that's the whole thing. And you can see the different explicit expressions for the topological codes. Okay. And this is another class of code called as color codes. So I'm going to skip this for now. Okay. But this is also similar to the surface code, except that we place the qubits on vertices and the checks on faces. Okay. And now a broader research in the recent days, attention moved away from topological codes to general LDPC codes. Topological codes are also LDPC codes, but then we move on with the general LDPC codes, because the problem with topological codes are they are zero rate codes. Zero rate codes means even if you increase the size of this lattice, like, so even if you make this this structure bigger, even if you make it bigger by adding more number of qubits, the number of information that can be encoded, amount of information that can be encoded in that will be limited. You cannot encode more and more information in it. Even if you increase, the amount will be finite. For example, surface code can encode only one logical qubit on its plane, on its structure, even if you add a now more number of physical qubits. So as n, so the rate is like number of logical qubits k by n, which is number of logical qubits by number of physical qubits. Now as n increases, k remains constant. So limit n tends to infinite, this rate becomes zero. So we call this topological codes as zero rate codes. Okay, and topological codes are very interesting because they have this fault tolerant nature. So the two properties that I have mentioned about fault tolerant, this topological codes possess those two properties. But the problem is they are zero rate codes. And so we go for quantum LDPC codes, which are non-zero state codes. And the interesting property is, if you have a classical LDPC codes, we can convert it into quantum LDPC codes. But classically good LDPC codes does not mean that they give a good quantum LDPC codes. So they may be different. And the parity check matrix that we get out will be sparse. That is advantageous because that helps in more simple decoders. Okay, and the fault tolerance too. Classically, it is only on decoders. Here, it helps in decoders and fault tolerance too. And the advantages are their low weight and finite. You can develop finite rate. People are working on developing finite rate quantum codes. And you can support, there's a larger theory for quantum classical LDPC codes that is developed for the last four or 5 decades. So we can use all this theory to quantum LDPC codes. We can port those theory to quantum LDPC codes. And the challenges is, good classically, if you say something is good, that doesn't mean that they are good in quantum sense. So classically good quantum error correction codes are not good classical quantum error correction codes. Classically good quantum error correction. Classically good error correction codes are not good quantum error correction codes. Similarly, classically good algorithms are not good quantum algorithms. Yeah. So you cannot port that directly. And we need fast and efficient decoders, which are under research now. We are working on to develop fast and efficient decoders. And the challenge is, we are trying to port the classical decoders to quantum decoders, but classically good decoders will not work in quantum systems. So we have to do some adaptations there. So one such example that we are working on is something called as belief propagation algorithm. Okay, so maybe I will take a short break. If you have any questions, please ask. Okay. So I believe there are no questions. So I will try to continue. So I will start with belief propagation algorithms. So suppose you have a 4-bit encoder state. Okay, or think about a classical bit. You have a 4-bit, and your channel will say that this bit is 0 with the probability certain things and 1 with the probability certain things. So it will say some probability of 1. It will give you some probability of 1 to the bit. Okay, so now what these bits will say is, it will pass this information. It will tell every checks. So these check nodes are connected to the bit nodes, and this connection is depending on the parity check matrix of the code. Okay, so I'm not going into the detail, but roughly the algorithm works like this. the bit nodes will share their belief about their whether they are 0 or 1. So that is, they share whether they will say that I am 1 with probability some p, and 2 will say that I am 1 with probability some p, and 3 will tell that I am probability 1 with some p. And they will pass this information to the checks. And the check will receive, say this will receive that 3 is with the probability p, it is, say with probability 0.1, it is 1. And this will be with the probability 0.3, it is 1. Now it has received a certain information. Now the check to have to send two information, one to bit 3 and one to bit 2. To bit 3, what it will send is, it knows about this check. This check is supposed to be 0, but the check that we computed should be 0. To make it 0, what should be the value of 3 given it has the value of 2? So it says that the probability of 2 is 0.3. The probability of bit 2 be 1 is 0.3. So it will say this, that you should be 1 with probability 0.3. Because the information that you received about other qubits, other bits, says that bit 3 should be 1 with the probability 0.3. And similarly, it will tell him that it is 1, it should be 1 with the probability 0.2, 0.1 in this case. And now when it is 2, when the check has only 2 bits incident on it, things look easier. But in case of 3 bits, it is not that easy. It should compute the probability of being 0 depending on these 3. Like that is, sum of these 3 should be equal to 0. It should be the probability that these 3 are 0, 0, 0 or 0, 0, 1. Oh, sorry, 0, 0, 1, 0, 1, 0, 1, 0, 0 or 1, 1, 1. These 3 should be 1, 1, 1. So it should compute all these combinations here. The probability of these being 0, 0, 1, 0, 1, 0, 1, 0, 0 and 1, 1. And these 3 combination will tell you that the fourth bit should be 1. So only then the sum of all these 4 value will be 0. It will maintain even parity. So to maintain even parity, these 4 cases, that the fourth qubit should be 1. And the other cases, remaining cases 0, 0, 0, 0, 1, 1, 1, 1, 0 and 1, 0, 1. This remaining cases, the fourth qubit should be 0. So you compute this probability and send it through this. These chances of these 4 probability plus add this 4 probabilities and find the probability and send it to this guy. Send it back. So which means check will tell the bits that with this probability you are 0 or with this probability you are 1. Okay, and then bit will follow back. So bit, once they receive the information about the checks, so they receive information about many checks. Many check will tell the bit that you are 0 with probability this and 1 with probability with this. And the bit 3 will do a majority logic. And based on the majority logic, it will say that I am 0 with probability 2. This probability I am 0 to the checks. And with this probability, I should be 1 to the other checks. Okay, so thus it will pass the information to and fro. Okay, and finally they converge to some point where which is close to that, and we can see that classically for a very good most of the LDPC codes, asymptotically this works well. This belief propagation works well. Though they are not optimal solution, they are suboptimal solution, but they work fairly well for a larger class of LDPC codes. Okay, and but there are problems in this belief propagation algorithm that are called as trapping sets. And for example, if on the pass, if this information about this qubit and this bit are lost, 2 bits are completely lost. Now the algorithm will not move forward. For example, the bit 2 cannot do anything on it because the 2 information is lost. Bit 1 also can't do anything because at least 2 information is lost. So if you want to send something to bit 1, bit 2, you don't have information about bit 3, so it can't tell the probability. It can't compute the probability. So these kind of, if your parity check matrix has this kind of structures, then you cannot continue the algorithm. It will trapped on these sets. So these sets are called trapping sets, and you cannot process it further. And the sad part is this quantum codes, most of these good quantum codes, this quantum LDPC code, they have these trapping sets. They have more number of trapping sets. So to overcome this, we do some post-processing. The people who work on, we work on this belief propagation, and we do some post-processing to get it better. Okay, and I'm not talking more about this post-processing, considering time and so on. And I will give a picture on how we understand this, the performance of this algorithms and the surface codes. So, for example, here x-axis represents the physical error rate. That is, the physical error rate represents the amount of noise present in the channel, and y-axis represents a logical error rate. This is the amount of error, the information that is getting corrupted even after doing error correction and some decoding algorithm. Okay, this is the amount of information that is being corrupted, and this size represents the size of your error correction code. So this is an example on surface code and applying belief propagation on it. Belief propagation with something called as ordered statistics and another post processing technique on it. Okay, and what we observe is, as we increase the block length below a certain point, if you see increasing the block length will improve the performance. That is, the logical error rate decreases as you increases the block length. After this point, there is no significant improvement, or more than that, there is a performance worsening. So if you see increase the block length, the performance worsens also. So this block point is interesting because as I increase the block size, I can push it further and further, and I can make it something like this, where this is 0 and this is maybe 1 or point by some number, 1 by 2 probably. Okay, and this point is interesting because if your channel is channel noise is worse than better than this in this case, then I can push it for more better. I can make it a perfect noiseless by increasing the block length. And if it is above this, then it is bad. It is worse. You can't do anything. So this point is called as threshold. And you wanted to design error correction codes or decoding algorithms. And this point depends on both error correction codes and the decoding algorithm that we use. And we wanted to design error correction codes and decoding algorithms so that this point is pushed towards the rightwards. And that is the goal. That is one of the goal of my research on error correction codes. Okay, and this book goes here, which means you can accommodate a larger class of channels, over channels too, and then your algorithms also performs better. Okay, and that is a point about error correction codes and fault tolerance. And finally, I wanted to give a perception on the quantum communication channel. And this is a simple, just like classical communication channel, this is a simple quantum communication channel. So, and these are the wide range of problems that lie in quantum communication model. So I'm going to skip this, but I just wanted to give you these are the research topics that are that I am interested in and that are highly involved in a quantum communication channel from a from a classical communication perspective. Okay, and with this, these are some of the problems that I am working on and I will be interested on to do further. And so decoders and code construction are mostly on error correction codes, and distributed storage is also about error correction codes. But the thing is, the code is distributed, so you put up your information on a nodes which are placed far apart. Okay, and you have multiple quantum computers; they are connected together using some connection, and you put your information on all these quantum computers together. And in classically, this Google, IBM, everyone, they use their Google and other Amazon, Facebook, and all those people, they put up their information in the distributed systems. And another research that I started recently is on quantum algorithms or quantum machine learning. And now I am working on reinforcement learning for some time for now, like roughly 6-7 months with some students. And I am planning to start working on quantum machine learning and algorithms affected by noise. I'm more interested towards noise, so I'm interested to see how noise affects the algorithm, how we can protect the algorithm results of the algorithm from noise, like whether the error correction code helps or should we go for another strategy like error mitigation or other things. Okay, and another interesting problem is like you have classical machine learning. And can we support quantum problems using classical machine learning? Like, can we develop a good error correction code using classical machine learning? These are some of the interesting problems from the quantum sense. And apart from quantum sense, I am interested to look. I am recently trying to look into this connection. Like, so you have classical information theory. So I'm trying to understand machine learning through classical information theory. So this is not classical quantum problem. This is purely classical problem. So we are trying to understand the classical machine, the machine learning problems, classical machine learning problems through the classical information theory. Okay, and still I am more interested to explore more on coding theory or information theory and communication and other aspects of signal processing, both classical and quantum. So my background is more on classical. I started quantum from classical perspectives. So I did my masters in signal processing and PhD in a specialized group where we focus on classical signal processing and communications. And there I started working on quantum error correction code from the classical error correction code perspective. So I am highly interested in finding the connection between this signal processing and communications to quantum signal processing and communication. Are some interesting problems in classical signal processing or communications like information theory and its connections to machine learning. Yeah. So that's all about the talk. If you have any questions, you can feel free to ask. And if you are interested, you can drop me an email and to this email. Aloysius at iitg.ac.in. You can drop me an email and you can clarify all your questions. And if you are interested in any collaborations or anything, you can drop me an email and find interesting. If you have any of your students who are interested in higher studies or PhD or higher studies, you can recommend them to contact me. Yeah, if they are interested in this lines, mostly directed to signal processing, communication or quantum computation, like quantum error correction. So if you have any other questions, you can feel free to ask.
Dear participants, if you have any questions or clarification during the session, feel free to post them in chat box.
So, shall we begin the vote of thanks?
Yeah. Thank you for inviting me. Like, so, yeah, I hope you have got some intuition about this. I am pretty sure that you would not have the complete idea of this algorithms and error correction codes, but at least you would have got an intuition about quantum algorithms and quantum error correction codes, which you can start and you can pursue further. Okay, so this will not directly help. It will indirectly help you to pursue further. And some of these slides are available on my web page also. Like, so the algorithms part is not there, but the error correction codes and communication perspectives are available in my web page. You can check those things. Okay. Yeah. Thanks. Now you can continue the vote of thanks.
Okay, thank you very much, sir. Thank you, sir. Okay, now,
Yeah. Thanks.
now I call Dharani to present the vote of thanks.
Thank you so much, sir, for your deeply engaging and informative session. It was very good explanation, sir. Your insights into fault tolerance mechanism have greatly enhanced our understanding of the reliability aspects of quantum systems. I now take this opportunity to deliver the vote of thanks. We express our heartfelt gratitude to our speaker of the day, Dr. Arun B. Aloysius, for generously sharing his time and knowledge with us. A special thank to our respected principal, Dr. J. Mageshwaran, for his constant encouragement and support. We also thank the organizing committee, our coordinator, and all the technical staff for their seamless arrangements. And to all the participants, thank you for your active presence and participation. Please don't forget to fill out the attendance and feedback form shared in the chat. We look forward to meeting you all tomorrow at 10 a.m. for another exciting session on topic the transformative impact of artificial intelligence on marketing technology and the prospective advancement through quantum computing. Thank you once again. Have a great day. Please, please.
Yeah. Can you stop sharing? I hope everyone who are interested have noted down the email.
Okay, thank you, sir. Thank you very much.
Yeah. Thanks.
I request every participant to fill out the attendance and feedback form.
So I can leave, right?
Yes, sir.
Okay. Thanks. Thank you very much for the invite.